About how the unit circle is developed. We obviously know it starts at 0 radians or 0 degrees, correct? And we finish at 2 pi radians or 360 degrees. Okay, did everybody agree with that? Okay. We also know that if I take, and you can do this a couple different ways, guys, but I'm going to work my way around the unit circle. I'm going to go from 0 to 2. Okay, I don't even care about the pi right now because everything's going to have pi in it. So let's just take pi out of everything. All right, and I know, and you know as well, that I'm just going to give you a visual of this for the first quadrant. Can I take the first quadrant and break it up into 30-degree intervals? Okay, and I'll get 3 of them, right? That gives me my 90 degrees there. Okay, so if I go around just counting by 30, maybe if I do all the degrees first, I'd have 30 degrees. This would be 60 degrees. This would be 90 degrees, right? Okay, there's going to be points over here as well. It's going to be 120 degrees, 150 degrees, 180, 210, 240, 270, 300, 330, and then eventually we get back up to 360, right? Is that pretty easy? You guys count by 30s? Okay. Zach, I know you're stuck. All right, can you count by 45s? $45 degrees. Add 45 gets me a 90 again, right? Add another 45. Okay, that would give me 135. Add 45 gets me to 180. Add 45 gets me to 225. Add 225 gets me, or sorry, add 45 gets me to 270. Add another 45 gets me to be 315 degrees. And then add 45 gets me to 360, right? Those are all the degree measurements that we're interested in. Those are all the degree measurements that we're interested in. I'm going to grab those and just slide them, because this is going to get kind of messy. So the ones that I can, I'm going to slide those on the inside. Tomorrow, I'm going to actually break it down into 2 circles for you, so that one of them, all you have to do is put in the angle measurements and the radian measurements, so degrees and radians on one circle, and then the second circle, you're going to put in the ordered pairs, just to eliminate some clutter. And I'll have it all designed for you so that you have plenty of room to write stuff. All right. I think writing one of these, creating one of these on your own, it's probably going to look like crap when you're done. Yeah, just to be honest with you. All right. So now what we want to do is we're going to go around and we want to put in the radians. Okay. I like going around, if I do the degrees first, I think most of us are more comfortable, finding those degrees. Now I'm going to do radians, and essentially, guys, what we're doing with radians is we're going to count the fact that we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 points, okay? If I look at just the red ones, I've got 12 points, right? Does that make sense? So I'm going to try to look at these red points, take my unit circle and divide it by 12 intervals, okay? So if you take, and we know all the way around gets me to 2, right? So if I take the interval from 0 to 2, 0 to 2, and divide it by 12, that would give me 1/6, wouldn't it? 2 divided by 12, that distance, 2 divided by 12, would give me 1/6. So what that tells me is that every one of these red dots, I can count by 1/6. So that's 1/6. This would be 2/6. This is 3/6. 4/6. 5/6. 6/6. 7/6. 8/6. If you understand that the denominator is 6, you're just counting to 12, aren't you, with the numerators? And then obviously this would be 12/6. Okay? Now if I look at these blue dots, the blue dots actually divide my unit circle into 8s. Okay? In combination with my x and y axes, divides it into 8s. So I'm going to take 2 divided by 8, and that gives me 1/4, right? So I'm going to start at 0, I'm going to add 1/4, and it gets me there. Add a 4th, it gets me here, which I already have as 3/6, but if I want to write 2/4 there, that's fine. Add a 4th to that, gets me 3/4. Add a 4th to that, gets me down here a 4/4. And then this gives me 5/4. This would be 6/4. This one would be 7/4. And then 8/4 again would get me back to 2, right? Does that make sense, everybody? That gives you all your radians. But now I got to put pi on them. So I'll put pi on that 1/6. I'll put pi on that 1/4. Okay, now 2/6 reduces to what? 1/3. So I'm going to reduce that, get my pi over 3. What is 3/6 or 2/4 reduced to? 1/2. So I'll put my pi with that. 4/6 is 2/3. 3/4 is 3/4. 5/6 is 5/6. This is just pi. 7/6 pi. 5/4 pi. This becomes 4/3 pi. This one down here at the bottom becomes 3/2 pi. This becomes 5/3 pi. 7 pi over 4. 11 pi over 6. And 2 pi. Is that something we can do? Okay. And I think we kind of maybe ran out of time yesterday at that stage. Okay. We didn't get into the next part. Now, I did finish the video yesterday after class, so if you do go back and watch it, everything's there. But I'm going to give you the same explanation now as I did there. Okay. We want the ordered pairs. Okay. We want the coordinates of these points. For instance, if I would take the unit circle out, let's see if I can. I don't know if one of these will do that. If I take the unit circle out of here. Okay. We're looking now, let me just clean those up. Would you agree that if I took the unit circle out, those points are just locations in two-dimensional space? They're locations in the x and y axes, right? You see these grid lines. We know that we're in the coordinate plane. So I'm looking for the directions to go from 0, 0 to that point right there. I want that x direction and the distance that's associated with it, and I want that y. Does that make sense, everybody? So that's what we're going to try to fill in here. When we do this, when we're working inside the unit circle, we're trying to find these distances. The only numbers that get used are 1/2, radical 2 or 2, and radical 3 or 2. Now, as decimals, obviously we know 1/2 is 0.5. That becomes 0.707. I believe this is 0.866. So you're able to tell which one's smaller and which one's bigger, right? If I were, maybe I don't have the circle here, or maybe neglecting the circle, don't pay attention to it if it bothers you. But if I'm starting right here at 0, 0, and I want to get to pi over 6, I would have to travel that distance, right? Okay. If I was at 0, 0, and I wanted to travel to pi over 4, would you agree that I'm traveling that x distance? And if I'm traveling from 0, 0, and I wanted to get to pi over 3, would you agree that I'd have to travel that x distance? Does that make sense, everybody? Okay. Can you tell me which of these is bigger and which one is smaller based on the size of those segments? The red one's going to be bigger, right? So what number over here of the 3 that we know we have to use is bigger? Yeah, radical 3 over 2 has to be the x-coordinate that goes with pi over 6. What has to be the x-coordinate that goes with pi over 4? Radical 2 over 2. What about the x-coordinate that goes with pi over 3? 1/2. Is that all right with everyone? All right, now let's talk about the y values. It's really the same procedure. Would you agree that that y value is shorter than that one, which is shorter than that one? So again, using these 3 values, doesn't this y value have to be 1/2? Doesn't this one have to be radical 2 over 2? And this one have to be radical 3 over 2? And I think, guys, that might be the most effective way for you guys to find those ordered pairs. Now there is, we've talked about the other relationships. We've talked that if I put the line y equals x through pi over 4, then the ordered pair for pi over 6 is the inverse ordered pair for pi over 3, so they just flip spots, right? The x's and y's interchange. If you look at pi over 6 and pi over 3, the ordered pair is just changed, okay? So that might be a way of you guys realizing that or determining which points are which. You should be able to go around and do your quadrants. So this would be 1, 0. This one would be 0, 1. Negative 1, 0 over here. 0, negative 1 here, right? Okay. Would you guys, and I'm not going to write all of them, but hopefully we see this. This point here, that color is maybe bad to use as a highlighter. That green point, which is that ordered pair, you guys agree that ordered pair is going to go right there? Okay. When I fold on the y-axis, it's going to go there. So this would be 1/2 root 3 over 2, right? But what is the only thing I got to pay attention to here? It's got to be a negative 1/2. The x has got to be negative in that quadrant. Remember, everything in this quadrant is negative, positive. Everything here was positive, positive. This is negative, negative. A lot of unit circles that are printed will actually have these things down here by the origin for you. If I'm looking at this ordered pair here, which is that point. Would you guys agree that it flips over here to this one? So this one's going to be negative radical 2 over 2, radical 2 over 2. And now we'll do one more. Okay, that point there, which is this one. Agree that that's going to come over here to 150, or 5, 5, or 6. And that would be negative radical 3 over 2, comma 1/2. Now, are all those points in the first and second quadrant going to reflect over the x-axis to give me the points in the fourth and third quadrants? Just pay attention to the plus or minus aspect of them, and you should be good. So that's something we can do. All right. I think, because I have been in this situation when I was in high school, my teacher just printed it out or said, hey, this is on page 280 in the textbook, and said learn. Okay? We're going to use that. We're going to recall these values. I think students are so much more able to use this and understand it if they understand how it's developed. Okay? It also helps with some of the other things that we're going to get into. Okay? Okay, so we're going to get into how the procedure of graphing what we call the sine and cosine waves, okay, or sine and cosine functions. So I'm going to write it this way. I'm going to find f, and I'm just going to write it of theta right now. If you want to write t, that's fine as well. I prefer to think about it in regards to the angle measurement. And let's just deal with the sine of theta. And we're going to do, eventually throughout the next couple of days, graph the sine, the cosine, the tangent, the cotangent, the secant, the cosecant. Okay? However, if you get a good understanding of what the sine and cosine are, the other four kind of fall in line with those, and use, along with a little bit of our college algebra, will get us the other four. So learning these two, then our college algebra facts should get us the other four pretty easily. What this says, think about what's going on here. On the unit circle, sine of theta is what coordinate? On the unit circle, that's what coordinate? That's the y, right? Okay. Theta is your input in this function. So your input is always your independent variable, right? It's in this case, the x-axis, or I'm going to write theta right here on my axes right now, okay? My input value is theta. My output value is sine of theta, which we know that is the y value from the unit circle. Okay? So every ordered pair that we draw here in a moment is going to have that ordered pair. Okay? Now here's the issue, and we're going to have to do some work here. Sometimes this is done for you. Sometimes you have to do it on yourself or on your own. What I want you to understand is that if you can count, because you've done it on the unit circle, you should be able to do it here. What we are going to basically do is take our, if you want to think about it as our t values or our theta values from the unit circle. So I'm essentially going to take this red arc, which hopefully I can make it as a circle. Take that red circle, and I'm going to cut it right here. Okay, pasting to it the radian measurements. Okay, so if I were just to look at you can also do it in degrees. It's just not common to see it done in degrees. If I was just to look at that thing right there, okay, with just the radian measurements, I'm going to cut this circle right here. I'm going to take that point of 0, 0, and I'll put it on the origin, and we'll stretch that cut circle out on the x-axis. Does that make sense? So when I do that, 0, 0 is here, and I would finish somewhere over here at 2 pi. So maybe 2 pi is there. 0 is there. Okay? Does that make sense? Okay? Now, if 0 and 2 pi are my starting and ending positions, go halfway and you should find what? Pi. Go halfway between pi and you should find pi over 2. Okay. Now this actually gives me, if you can't remember what this, because we need this interval over here as well, we need that point there. If you can't remember what it is, this one here close to the x-axis has given you a counting tool, because that's 1/2 now, right? 1/2 pi. So 1/2 plus 1/2 plus 1/2. Well, that would be 3 pi over 2, wouldn't it? 1/2 plus 1/2 plus 1/2 is 3/2. Is that doable? Okay, now let's draw a comparison back to the unit circle. The unit circle gives me, looking at just maybe the pi over 6 increments, it breaks the first quadrant up into 1, 2, 3 spots, right? 3 intervals, 3 sectors in a circle set, kind of definition, vocabulary use. And that's between 0 and pi over 2, right? So when we stretch this thing out on the x-axis, between 0 and pi over 2, there should be 3 intervals. Does that make sense? So what I'm going to try to do is I'm going to try to break this thing up into thirds. And we know that this one would be pi over 6. This one would be pi over 3. Is that okay with everyone? So I'm going to, now this here, there's my counting tool. That distance between the y-axis and the first marking, or I guess any marking, would be my counting tool to replicate that distance. Does that make sense? So 1/6, 1/6, out of that, another 1/6. This is 3/6. So this would be 4/6. I'm going to write as 2 pi over 3. This here would be 5/6. Okay. Keep adding 6. So that would be 7 pi over 6. That would be 8 pi over 6, which is, I'm going to write as 4 pi over 3. Okay, so that was 8/6, so this is 9/6. This would be 10/6. So that's 5 pi over 3. This would be 11/6. And my 2 pi went 1, 2 short. I'm not, guys, I'm not too concerned right now on your scale, but we want to try to be as accurate as possible. So all those are evenly spaced with one another, right? Okay, so I just counted by 6 all the way from 0 to 2. Okay. Now in between the red ones should be my increments for pi over 4, right? So pi over 4 is there. Pi over 4 should be there, so that's 3 pi over 4. 5 pi over 4 is between 7 pi over 6 and 4 pi over 3. And then we've got 7 pi over 4 right there. Now it gets cluttered, right? And I know, I apologize for those of you that are sitting in the back. It might be kind of hard to see. I apologize for that. But that is simply just taking the circle with the radian measurement stuck to it, those distances, and then taking that circle and just stretching it out on the positive x-axis. Okay. Now we can replicate it. We can reflect that on the y-axis, and we can go in the negative direction. Does that make sense? And we will eventually. Okay. And we can actually cut and paste that between 0 and 2 pi and attach it at 2 pi, so it goes from 2 pi to 4 pi, right? And keep cutting that setup and the pieces and pasting it to go from the larger values of pi if I need to. Okay, we will eventually. Does that make sense? Now, eventually, guys, the reason we put all those in there right now is just to kind of prove a point of what we're doing. Eventually, we're probably just going to look at the blue ones and probably just look at like a half of those blue ones. Okay? Look at the ones like 0, pi, 2 pi, those are pretty easy. Pi over 2 and 3 pi over 2, those are pretty easy. Those are probably the ones that we're going to look at for the most part. Okay? So, what are we going to do? We initially started talking about the fact that when we graph the sine function, the ordered pairs are some theta and then the y value from the unit circle. Okay, so it's going to be a good idea to have your unit circle next to you when we're looking at this. And I'll jump back and forth a little bit. But the first one I'm going to do, I'm going to say theta. Okay, let me slide this stuff over. Okay, let's say that we're looking for f of 0 radians. That would equal sine evaluated at 0 radians. Does that make sense? So this, remember, this is your input. So that's your independent variable, or if you want to think about it as your x value for this graph. And then whatever this evaluates to off the unit circle, that's the y value that goes with it. So when I look at the unit circle, and I want to find what the y value of 0 is, the y value of 0 radians is the blue one, right? Let me zoom in here so you guys can see this a little bit better. All right, so the y value is that 0, correct? So that's what I'm going to pull out and let be the y value for this function. Plot 0 degrees or 0 radians, comma, 0 in the y direction. Okay? Now, so that's my first order pair, and this might be something that we might want to do as we set up the x-axis. We kind of neglected the y-axis. Looking at this, look at that 0. Look at that 0 right there. As I start going around the unit circle, what is the largest that y value becomes? 1. What would the smallest that y value become? -1. So when I transfer these values over to this curve, the biggest value I got to worry about is 1. The smallest one's -1. Now when you do this, give yourself some room. I don't want to put 1 right there. Does that make sense? Okay. Go to the top because you're not going to be above that. So go to the top of your y-axis and put 1. So we're going 1, 2, 3, 4, 5, 6. I'm going to use, should be 8, be okay. 8 blocks here for my 1. And then 1, 2, 3, 4, 5, 6, 7, 8. And those things, guys, are just, because I've done this enough times, I know that we don't want to scrunch everything up. So just give yourself some room. Thinking about the way we did the x-axis, if we were to put 2 pi where pi is, things would have gotten condensed a lot, right? We had a lot of just garbage overrunning into the same spots. So now what we're going to do is we're going to try to create a list of values. Okay? Let's go to the next angle measurement we come across, which would be pi over 6, right? So we'll come up here, we'll take that 0 out, and we'll put pi over 6 in. Pi over 6, so the pi over 6 is my horizontal coordinate, and then I evaluate sine of pi over 6. What is the sine of pi over 6? It's 1/2. So now that's the ordered pair that I'm going to plot. So you're going to find pi over 6, and I find 1/2 on my y-axis, and it's that point right there. Okay? The next one then would be pi over 4, right? So I'm going to evaluate f of pi over 4 equals sine of pi over 4. My x-coordinate is going to be what? or my input coordinate, my horizontal coordinate, however you want to refer to it, it's pi over 4, right? If I evaluate sine of pi over 4, what does that give you? Radical 2 over 2. Okay? Now, here's the thing. Radical 2 over 2 is, it's about 0.707. So I got to find that on my y-axis here. Well, I know if I cut that, that was a half. That would be 0.75. So I'm just going to make a mark here just below. I'm going to say that marking right there is radical 2 over 2. Okay? Not a big deal how accurate you are here. We should get kind of a ballpark image. But pi over 4, I'm going to go up and find the radical 2 over 2. Get that point there. Is that doable? All right, let's go to the next one. Next one would be pi over 3, right? So I evaluate pi over 3 for the sine function. So pi over 3 is my independent variable. Then the y-coordinate becomes radical 3 over 2, right? It's the y-coordinate on the unit circle when you have pi over 3 as your t value or your theta. Now, that number, that's 0.866. So, just kind of estimate maybe 0.866 is there. So that one is radical 3 over 2. So pi over 3, maybe that point there. Okay, and to be honest with you, in mine, it's probably maybe there, and I've probably got some other things that could be adjusted, but that's good enough. All right, what is the sine of pi over 2? That'd be the next one we're looking at. That's 1. That one's an easy one to graph, right? Okay, so we're getting a series of points, right? So essentially, guys, what we're doing here is like saying that if I was to graph like y equals x squared, we know that maybe integers are good numbers to use for x, right? Those are good numbers to use as your independent variables, okay? 1, 2, 3, -1, -2, -3. But we could have also done with x squared, I could do 1/2, I could do 1/4, I could do 1/6, I could do 2/3, I could do all those numbers, right? But squaring those numbers, like squaring 2/3, gives me 4/9. So we know 4/9 is kind of a pain in the butt to graph on the x and y axis, right? So we usually wouldn't use those. Initially, I want to show you all the points, okay, or a good series or amount of them. But eventually, guys, we're going to say, what are some 5 really nice, easy points to graph? Would you guys agree of the ones we just graphed, 0, 0 is pretty easy, and pi over 2, comma 1 was pretty easy, okay? So those are some critical ones. Those other 3, those are going to be ones that we don't necessarily independently graph, but if we draw the curve correctly after plotting 5 or 6 critical points, those should lay on the curve. Does that make sense? Okay, they should fall in line. But I want to show you guys some symmetry here. What about going back, or let's look going back at this thing here, okay? If I'm right here at what ends up being pi over 3, and then go to pi over 2, okay? We in our function we've already graphed that point, okay? Because of symmetry, don't we start going back down when we get to that y value of radical 3 over 2 again? So this point here had a y value of radical 3 over 2. We hit it, go to the maximum, and then we start going back down through radical 3 over 2, right? So because of that, we can use symmetry to say this next point here of 2 pi over 3, instead of maybe evaluating, looking at my unit circle, isn't it going to be the same as that point right there? Okay, so 2 pi over 3, I'm just going to align, I'm going to find that x value, and I'm going to align it with this point right here. Okay, so then 3 pi over 4 should align itself with this one here. 3 pi over 4 should align itself with radical 2 over 2. And then 5 pi over 6 should align itself with the 1/2. Is that okay with everybody? And if you go back and you look at your unit circle, 5 pi over 6, the y value that goes with is 1/2. 3 pi over 4's y value is radical 2 over 2. 2 pi over 3's y value is radical 3 over 2. So we are still evaluating here. That symmetry idea is just a little bit easier. Okay? If you think about it, that right there, that line is kind of analogous to that right there in the unit circle, right? Does that make sense? Okay. All right, so what's the y value at pi? 0. Okay, so plot that point. Even going back to this, let's look at, so we're in the second quadrant here, all right? And this y value is 1/2, right? What's the first y value going to be over here? Negative 1/2. So it's the same same quantity, it's just opposite sign, right? So this point here, which was 5 pi over 6, had a y value of 1/2. So 7 pi over 6 could have a y value of negative 1/2. Okay. Now, just to kind of expedite the process here, let's not go through and find all of these, but hopefully you get the idea that there are a lot of points in here, and they're just being generated by your angle measurement or your t distance, comma, your y value from the unit circle. 3 pi over 2, what would be the y value of 3 pi over 2? Negative 1. What is the y value of 2 pi? It's coterminal 0, isn't it? So 0 and 2 pi have to have the same ordered pair. So now that we've done that, we have a bunch of points that we can draw a smooth curve through, right? Now it's got to be a smooth curve so that we, it's like if I asked you to draw the parabola, if you only did 3 points, you don't make a V, right? You understand how parabolas look. The sine function is going to be, I don't use that big though. I guess I have to. We're going to a smooth curve that passes through those points. So it takes a little bit of time maybe to get that picture right. I get a lot of people who want to do this. That's not the sine curve, right? The sine curve is not linear, okay? We'll look at the purple one here. And it's generated simply by taking your t distances around the unit circle, or your theta measurements, and plotting them against the y value from the unit circle. Okay? How do you think I get the cosine curve? Do the same thing, but now my y value on the graph here would come from the x's on the unit circle. All right, and we'll do that. We'll do that tomorrow. The tangent would be found by plotting against the x-axis your angle measurements again, but then you take your y value off the unit circle and you divide it by your x value off the unit circle, and whatever that quotient is, you plot as your y value in the coordinate plane here, and you get these curves. Okay. Now, what I want you guys to realize, let's kind of talk about this as because we know that the sine function and the cosine function have a domain of all real numbers. These things go on forever in both directions. Okay. So what we just came up with is just a kind of a cropping of the sine curve. Okay, so I like GeoGebra because I can actually force it to put my radians in on the x-axis here. But if I type in what we just did, okay, I just type in sine of x. That's the curve that we just came up with, and we came up with just kind of that picture there, right? Okay, but this thing is referred to what we call periodic. Okay, meaning it does the same thing in both directions forever, right? Okay, but if I look at just sine of x between x being 0 and 2 pi, it's that red curve. Would you guys agree that if I take that red curve and start cutting and pasting it and attaching it to its endpoint, so cut this out and paste it right here, it would give me this green section, and then it would do that again, it would give me another green section. I could keep doing that on and on and on forever. Okay, that's what we refer to as a periodic function. Now think about this. If you fold the y-axis right now, visualize that in your mind. What happens to the red curve if I fold on the y-axis? Think about that, okay? Now that you have that picture in your mind, fold on the x-axis. Does that red curve go on that green curve in the second and third quadrants? Does that make sense? Okay, so let me see if I can do this. I don't know if I can do this. Let's reflect this on that axis there, and it gives me that, right? Now let's reflect that on the x-axis, and it covers up the green curve, right? That means that's an odd function. Does that make sense? You guys remember seeing odd functions yesterday, even odd properties yesterday? We'll start off with that tomorrow and talk about that connection. Thank you, too.